everyone. And also I'll thank my PhD supervisor, Professor Lakshmidhar Behra, who gave me this opportunity to come here. It's always a pleasure to come back here, and I feel privileged. And I'm honored that he still thinks I am, worthy enough to be invited. So, okay, so what I'll do is that I'll just talk about some of the work we are doing. So, basically, whatever you have gone through the whole day, so I'll just try to show some of the applications of those things. So basically, I'll not be deriving any equations or anything. Probably, I will just talk about some of the methods and show you some videos. And while I do that, I'll also provide some motivation for all the work we are doing. So in the process, I'll be using some of the videos which are available on the YouTube, so they are not mine. So yeah, that's just a disclaimer. So with that, I should begin with my presentation. So this is. So I should tell you something about my company. So as you know, TCS is a IT MNC company. It is the largest Indian-based IT company, and it is placed among the big 4 most valuable companies in the world. So it has been recently ranked 57 in terms of the innovation by Forbes World Most Innovative Companies, and we are the 10th largest IT service providers in terms of revenues. In terms of R&D, I should tell you that we are the largest R&D group, industrial group in the country. We have 19 labs in 3 countries. We have more than 1,000 co-researchers with about 100 PhDs. We publish, recently in financial year 14, we published more than 400 journals and conferences, and so far we have filed 1931 patents. So yeah. So I am based out of Delhi, it's quite near. So my group, I belong to the MGR research group, which stands for Multimedia, Graphics and Robotics. And we have around 4 PhDs in our group. Okay, and we have close collaboration with IIT Delhi, with IIT Kanpur. Okay. So these are some of the projects that we are working on currently. I'll go one by one. Okay, fine. So as I told you that I'll provide you motivation for each of my research. So this is the first video. I hope the video works. Yeah.
Groups and with people and with startups and organizations that no one would think Lowe's would work with. My name is Kyle Mell, and I'm the Executive Director of the Lowe's Innovation Labs. Lowe's Innovation Labs is here to build new technologies to solve consumer problems with upcoming partners. We focus on making science fiction a reality. Retail really hasn't changed much in the last couple hundred years.
They could think
Robots
maybe
are the first thing that can really change the customer experience.
Pushbot, the orchard store robot helper. What are you looking for today?
The robot will come up to you and will say, hi, what can I help you with?
Where can I find more of these?
I'm looking for hammers.
Me gustaría comprar esto.
Can you place the object in my viewfinder? Is this the item you're looking for?
Yes.
I'll take you.
Once you show the robot the item, it will then navigate you to where that item can be found.
The robot has multiple sensors and is able to navigate inside of the store. It creates a map overnight. So the next day in the morning, the robot knows where the products are located.
I'll take you to the Plum 16-ounce flat contoured handle hammer.
One of my favorite parts of the robot is its ability to speak multiple languages.
So just a motivation, you can check this video on YouTube. So what you saw is that if we want to have such a robot which can help you in finding a product or probably identifying the location where it is located or guide you there. So what do you need? You need effective human robot interaction. For example, when you are speaking, it should be able to understand you. If you are showing something, it should be able to recognize you or probably greet you when it sees you. So so for this we'll have to develop a lot of algorithms. So that is what we do in our lab. So some of the examples of what we do is I'll discuss here. For example, we tried implementing like gesture-based control, which will have done it already. So what we do is that you can remotely control a robot just by using gestures or hand movement. So just to show you what we can do is just see a video. So we have a Kinect here. We extract the skeleton. I hope it is visible there. So
Stop.
once you make a movement, the underlying process, you all know HMM and other things are there. Many learning algorithms go into it. So I'm not going to do that. Just show you the output of all this works. So this is one aspect where by which you can interact with a robot. So this is one thing. Similarly, you want, sometimes what you need is that, robot should follow you to the place, right? So that let's say you are in a retail store, you have a robot. So and you don't want to carry all the items that you are picking up from the shelf. It will be good, if you have a robot that follows you and you just go on putting the things. So for that, you probably need something of this kind of algorithm. So what you see here is, we have a tracker that tracks the person under different conditions, and then a robot is there that follows you. So these are this is another way the robot interaction is useful. So what we did is that we combined all of these things into a single application, which we called a T-serving robot. What it basically does is that it follows a line on the floor. It recognizes your hand when it approaches the robot, and if you are blocking it, it will not hit you. It will wait for you to go away, and if the tray is empty, it will tell you that the tray is empty or something like that. So So what it does is that it counts the number of cups it is there. It also recognizes whenever you bring the hand and to pick up your cup, it will stop and greet you. And then we could have used a autonomous navigation. We have the mapping and planning and things like that. But we still use this. The reason is that in the offices, our spaces are very restricted, and we want accuracy, very high accuracy. So you can see that we have a controller here that looks downward. There is a camera is there that looks downward, and there is a controller that always ensures that you are on this light. So it's a simple PID controller we deployed here. So it always ensures that you are on the light. So this method is very precise, and it is useful in the material handling industry where such applications are required. So I hope the people are aware of the Kiva systems, but they use a different technique. They do not use these color strips. They use probably RFID and other things. So this is one application that we developed. So how the hand is detected is like this. What we did is that we learned the model for the skin color. We call it a Gaussian mixture model, and using that we learned the model. What you can see is that it only recognizes the hand. Even if you are wearing the shirt, it does not recognize it, or your cup is that doesn't recognize it. So in that way, through all these things, we made it very robust, and this is how it identifies the hand the moment you approach it. Then it stops and greets you this way. Okay, similarly, this is how you train to identify empty or non-empty. What we did is that we used an SVM classifier and trained, we just took a grayscale image. That was good enough. And we took a lot of images of filled images with cups and without cups, and trained it to learn one of them. And all of them are running in parallel. We used all these threads and everything just to make sure that everything is happening in real time. So so the second problem that we have been working on, I told you that again, if I have to go back to that first video where the robot has to navigate all around your store, we need to have this capability of building the map and localizing itself in the map. So just to show you that how the whole thing looks like, just a simulation, gazebo simulation, it shows like, okay, what does the mapping and SLAM means is that you have range sensors, and as you get the data about like where the obstacles are there, you go on building the map. At the same time, you localize yourself, you get to know where you are. So this is the normal SLAM thing. So we do. So now the problem is that if I have to build a map of the environment, let's say not using range information, like humans like us, we do not use range information to build a map. So what happens in our case is that we remember the places in terms of landmarks, like I have seen a tree near the building, or there is a road near the building, and this is how we build a map of the environment, right? We do not use range information like laser or things like that. We have some sense of distance because our time, like how much we move, but still, you know, mostly we remember things by like images, right? So that is something we want to do here. So I am just showing you the result, and then I'll go into the method. So this is called topological mapping, where our task is that you take the images using cameras. So this is the camera view of the robot, and as the robot is moving in the let's say lab or whatever, so it creates a graphical map of the environment. So this is not the it does not have any geometric information. It doesn't have the sense of distance traveled and things like that. It only things have the nodes which are these are the nodes. Nodes are the landmarks. So this each node is represented by an image. So every image which is a new one is a landmark for me. So it decides how many nodes are to be created, how they are to be connected. The biggest challenge here is to find the right loop closure. Loop closure means that you are coming back to the same location again. If you don't do that, you will never be able to build the map. So there we have this problem of perceptual aliasing, which is very well known. Like it is very easy to get confused when you cannot differentiate between two places. I can give an example. Let's say you get into a building, and sometimes what happens is the building is very symmetric, so you get confused with the two corners of the same room, right? It happens. So that is a perceptual aliasing problem. So we have developed an algorithm. Basically what we did is that we the current they mostly use the features independently. What they say that not independently, they take into account the fact that the features co-occur together. They are together. For example, a tree and probably the road goes together, or maybe a book and the table goes together. As long as they are together, you say that same place. But they do not take into the spatial distance between them, like how far is there. Either book and table, are they near or far, or maybe they are two different places, or maybe same places. So that aspect we take, and we define something called word pairs, where this is how we define the word pairs, and this word pair is directional in nature, in the sense that if A is a pair with B, not necessarily B is a pair of A. So that is what we say, that in this case B is within the neighborhood of A, so AB is a pair, valid pair, but BA is not, because A is not within the whatever the scale size of B. In this case, both C and D and DC are valid pairs, but in this case, none of them are pairs. So this directional attribute provides us more discrimination to distinguish between the loop closures. So I hope there is a green line, you can see it. So what you are trying to say that this is what happens when you simply use the fact that features are there, their spatial location you do not take into account, the red one, while the green one is the one that happens when you have the word pair. So what you are saying, I'm telling you, I'm defining the problem. This is the node index. So you are saying in my map there are 25 nodes, and this is saying that I have got a query image, means the new image comes, and you say with whom it is matching, like how similar it is to existing nodes. So my previous algorithm says that all three, that means probably the 7, 10, probably 12. That means for the query image there are 3 candidates. All could be a possible loop closure candidate. But after incorporating the spatial information, my likelihood changes to this, which says this is the only loop closure. That is the matching is good. Others are not. You see, others are actually it is reduced. It's not visible here. It is reduced here, and it has gone up. So the spatial information is giving us the better discrimination in order to detect the loop closures. And we showed that by including the spatial information into the our algorithm, our performance improves. That means improvement in the performance improves when the quantitation error increases. Quantitation errors is basically is there whenever you discretize any signal, that we all know, right? So if your dictionary size is large, that means your more and more features are there, that means your quantitation error is less and less. So but if you are going for a higher number of features, your computational requirement will also go up. So probably you will always like to work with lower number of features, discrete features. So when we go for lower number of features, your difference between the let's say only word and word pairs increases. That means we are performing much better when the quantitation error is very high. So this is very good. And when it is you are going for very large number of features, this is the large number of features, then your it doesn't matter whether you are using pairs or not. So we compared with the various methods that are used in the literature, and we have shown that now we are the best among all the methods. So this is currently under review. I hope it gets accepted somewhere. Well, so so we did some work with the tracking. I showed you in the human following thing application, the tracking is an important part of it. So we did some work with one of the students from IIT Kanpur itself. So so I'll come to that. So one of the work that we did is that while in most of the cases we treat tracking as a object tracking problem, that means you don't have to specifically tell whether it's a person or an object, because the only thing that you are worrying about is a bounding box, and whatever the features are there, that is what you do all the time. Okay, you want, as long as you get a matching of both features, then you say that the person is there. This is called tracking by detection framework. Now the problem is with humans is that when I say humans, I am talking about there's a particular shape is that. So how do you incorporate the shape into that bounding box and tell that it's no more a object only, it is also a human. So in order to do that, we had to use color and everything, but on the top of it we imposed a graphical constraint by saying that okay, we can have three let's say colors, and you just take the centroid of that, it kind of a node, and then you can connect them by some edges, and you call them a graph. So next time when you detect, for example, if this is the case, can you detect the partial occlusions, which is a cause of major problem when you do a tracking.
Yeah, I have seen that, sir. Yeah, thank you so much.
So just see the consider. This is the normal case. In the normal case, what you are saying that there are three nodes, they are connected to each other, and this is a right ideal case, right ideal candidate. But when you come to partial occlusion, you see even though you have some detection here, my graphical constraint is saying that this is the valid connections, this is not to be connected. So in that way, even if it is partially occluded, we are able to detect the person. Same thing here, you see the head color matches, the jeans color matches. So in spite of that, we are still able to detect this lady, which is partially occluded. This is a very severe case. It is very difficult to detect such cases, but we could do that because we could impose a graphical constraint on that. We use a MRF based graph matching algorithm to do that, and all these cases we could resolve, right. So I'll show you the outcome of this one. So what you see here is first of all, there is a lot of occlusion is there. There is a camera motion is there. Okay, probably out of pose rotation is there. That means person is completely rotating in a vertical plane. So in spite of all that, and white one is the predictor. Whenever you get occluded, use a predictor to one, and red one is our tracker. So in spite of all these occlusions, camera motion and everything, we could track the person successfully. So okay. So okay, there is another algorithm, probably another video. So you see this person is moving under shadows and everything, and camera motion is there, lot of clutter is there. In spite of all that, we are able to track the person successfully. So the main challenges comes like recovering from the occlusions. Once you lose the target, again recovering them is very difficult. So But anyway, this is one of the success of this algorithm. So now extending that one, well, you had one person, but what about like you have multiple persons in the same frame? So where the application comes is that, let's say today we are talking about autonomous vehicles, right? We want the vehicles to move on its own. So if there are multiple people on the road and somebody is trying to cross the road, in that case it is very important to track these people so that you can know the intention, whether this person is going to cross the road or not going to cross the road. So you cannot simply treat them like static objects, but also you have to see that whether follow them, actually basically track them. So in this case we recently did some work. The idea was this is the problem. So the main problem comes is that, see here, when you have multiple people in the video, they all look similar to you. It's very difficult to differentiate them based on color and things like that. So what we do, one of the major problem is called ID switch. In a sense, what happens is whenever the two persons cross each other, the chances of the IDs getting switched is very high. For example, without the occlusion reasoning scheme, this is called occlusion reasoning scheme, so that you can resolve this association. If you don't have this, what happens, once they cross each other, the IDs are interchanged. Here the lady had ID of 2, now it is becoming 1. So, but if you have a proper reasoning scheme, then probably you can avoid that. So this will lead to longer trajectories, the trajectory fragmentation will reduce and things like that. So how you do it, one of the standard method is that you define the the process is called tracking by detection. So you apply, let's say, person detector on each frame. So you know the candidates, the potential candidates in each frame. Once you have that, then you kind of compute the affinity matrix between them in some way. You can define these parameters. You can define. This is how I define it. I have taken the overlap and the color histogram as one of the measures. You can include all other aspects into it. Once you do that, then you solve as a binary optimization problem, because see, these are the source of conflict, because what is saying the similarity of this agent to it is similar to two cases, like one in the previous 0 and these 2. Similarly, okay, so this is good. In this case also, in this case the agent 0 is now similar to, let's say, 2 or 4. So these are all sources of conflict. You solve them and find one-to-one relationship by this binary optimization, solving this binary optimization, and what you get. See, this is the current detections, this is the predictions that you got from the previous frame. Compute this matrix, solve the this optimization problem, get 1:1 association, and that you say is the identity. Whichever is not detected, you say that it's a predictor, and you just go by the whatever predictions you got. So so this is how we solve it. Okay, so this is some other things. Okay, so just to robustness. So this is how it looks like. So the green ones are the correct trajectory that we have generated. That means if you are, these are the parameters by which you evaluate the performance of a pedestrian tracker. So this is MT means mostly tracked trajectories, green ones. That means more than 80% should be tracked. So all the green ones you can see this is MT. PT is a partially tracked trajectory. That means less than 20% should be tracked. Not. ML is the mostly lost, that means less than 20% is tracked. Partial tracked means between the MT and ML. FT is a false trajectory that is generated because you have identified the person wrongly. So whenever there is a cross, whenever there is ID switch, you see these false trajectories. So this is how we evaluate, and so when we compared initially, we saw that we are very bad compared to the state of the art. So even though we had some novel idea, but we didn't do very well compared to what people have reported. So what then we did is that we took the arrangement of people in the images. What we believe is that, I showed you that we also have a camera motion. So what we believed is that the arrangement of people in images do not change very immediately between the consecutive frames. Okay, so the arrangement of people will not change from one frame to another so easily. If we exploit that, probably many of the the ID switches and association error could be solved. That's one. Second is, if you are in a group of people, each agent has a unique relationship within the group. So if you can check those associations, probably you will be able to avoid more of such errors. So what I mean to is that the first one is a special information. Here also we are using Markov random field based graph matching algorithm. So what we are saying, let's say your source, that means a previous image had this kind of layout. Now in the current frame you did a detections and you found that this tree is coming here, right? So based on this graph matching, you can easily say that this is a wrong match, shouldn't be there. So you can avoid that. So this is done by the your graph matching algorithm. So based on that, you can associate the IDs, and whichever is not detected, you use the tracker. And this one is start a new agent because it says that anyway it is not matching with anyone previously. It is a new agent. It will disappear if it does not arise in every frame. So, but at least we are able to get rid of this wrong detection what we got. This was the use of spatial arrangement. Now, relationship within a group. So you see there is this person is a agent 2. So as it crosses through this point, it get not detected here. After that, it assumes a new ID called 7. Okay, see, this happens because it is going through conclusion and so many things are happening. But if we exploit the fact that while it was crossing, 2 was crossing, you see it was close to 0 and 1. Okay. So when it comes out, when it's not detected and you are again detecting to see that you can see that it is close to 0 and 1, then the person should be 2 only. It cannot be 7 or anything else, because in the previous frame they were close to 0 and 1. You are moving together. Suddenly you cannot disappear. It's a physical system. So then we could recover that one. So as you can see that now we have done much better. That means the red ones are the bad ones. So now the red ones are less. So in that way we are performing better now by doing whatever we did. So just to show you how the whole thing works is, so you see the person is being detected and we track. So these are the trajectories we generate. So see, if our detector fails, we cannot help because we are assuming that our detector has to be correct. We are only focusing on the resolving the associations. So the lady is tracked properly, everything is that. There will be an error here somewhere. Tree is tracked, this is wrong. See, this is a wrong detection, but we don't care because we can't help it. We are not working on the detector currently. So yeah. So see another person. You see all these persons have been tracked, and you see yeah. So there is a lady, you see that she will cross through the entire frame and we are able to track her successfully. This is one of the plus points of our algorithm. There are many minus points, but this is the wrong detections, like we can't help it. But so more.
So many they are not detected.
Yeah. So if it is not detected, I can't help. So you start with the assumption that your detection is working. But once you are detected, your task is to ensure that you are tracking it thoroughly. You do not lead to trajectory fragmentation or ID switches. So that part. So you see you have shadow. See, there is a person who is detected on the shadow itself. So there are a lot of problems are there. It's a challenging problem, and a lot of people are working on this. The lady goes inside, still comes out, still we are able to do it. But there are many cases where it doesn't detect. So still not the best, but yeah. So initially you will see there were long wrong detections and trajectory fragmentation, but once they are close enough, then we are able to do it. See, you see detected and then it disappears. These are all. But now after this, you see all will be tracked properly. So we still have to improve on this, and yeah. So, okay. So well, now I will come to the another application which is related to robotics. I think we had a very good session today where we learnt about inverse kinematics and things like that. Probably one application is here. So what I am saying that the industrial automation, as people said, is that people said that it is solved completely. There is nothing to be done in the industrial automation side. What you have to do is service robotics and whatnot. People are talking about, but not. The industrial robotics is also changing. How it is changing? I'll just show you how it is changing. Then probably we'll. So what this robot does is that it does some assembling of some electronic parts. Okay. So you have a conveyor belt, something is coming, and the robots are picking up items, you see, and they're pretty precise, and so what does it say? It says that they're pretty autonomous, isn't it? They're pretty autonomous, they're very intelligent, and they can do everything on its own. But unfortunately this is not the case. Unfortunately this is quite mechanical in nature, in the sense means that probably you are telling it everything to do itself, but everything has been told to itself. For example, how much it has to move, where to place, everything has been hard coded on CNC machines or computers, everything has been hard coded. So but this automation is possible because you have a very huge system that is called assembly line. Somebody is picking up one item, somebody is bringing it, then your robot is picking up exactly from the same location. If there is an error in that place, it cannot recover. But the whole system is made in such a way that everything looks very fine, and everything happens like that. So this was the old automation so far we did, and here we are very good, almost 100% of today's industrial automation is just like this. You have assembly lines where the robot precisely does what it has to do, no human involved, at least in the assembly lines, and this is how it is happening. Now see this. So there is a robot, it sees, this is from IEEE Spectrum, you know that Baxter robot, everybody knows, right? We'll go into this one, will not. First of all, this robot has the ability to see things, perceptualize the objects in the workspace. You can teach the robot how to do things, and it can pick up the item, whatever you say, it can do to a limited extent. It will not collide with you. There is no cage, as you can see. Earlier we saw that the robots were confined within cages, but here you do not have any cages. They are working together with the person or whatever. Now it seems for a moment that we are going backward, isn't it? In the previous one we saw a robot which was very fast, automatic, doing everything fine without any human intervention, very fast, probably very accurately. But here it is what, like it is, you have to probably, it is very slow, it does not seem to be doing very fast, and probably, doing very rudimentary task compared to what we saw that. But it is not the case. The case is, now why it is needed? The question is that why do we need to go from the first and the second stage? The need arises for the fact that today our robotic automation is limited to only big factories, like automation industry. Automotive industry is the one that uses robots for most of the time. It is because it requires a huge investment. Why investment is required? Because you will have to establish the entire assembly line, that the one I talked about. So that requires very huge investment. So let's say you have a small and medium enterprise like cottage industry. Let's say I want to manufacture a phone, and I want a robotic system to automate this assembly of phones or something like that. I can't afford that. I cannot invest on setting up such a huge infrastructure. So but what I can do is that, let's say I have a robot like this, small robot, it costs only $25,000, and I teach it basic task to do it.
The same robot by the Rodney Brooks?
Yeah, Rodney Brooks. I think robotics, Rodney Brooks. So the advantage is that you can teach it basic things, and you can take it and you can train look, pick up this from, this is how you assemble, this is how you put, and you tell it to repeat it 10 times. So you don't have to put the entire assembly line, right? So this is how it is going to change. So now, even though you are a small manufacturer or small cottage industry or something, you will be able to take the advantage of your robotics revolution. So there is a concept called factory in a day. In Europe they are trying to popularize this concept where you can lease the robots. So you just call the person that, look, I need a robotic system for, let's say, 1 month, and they will call in the morning. Within one single day they will set up the everything. So you can just start working the next day and assembling and everything. So that is possible if our robots are intelligent. They can work with humans, where humans can teach them by demonstration. You have perception, touch sensor and everything to make sure that even if there is an error, that can recover from that one. So that is how the automation will change in the industrial domain. So in this, after I give you the motivation, I just wanted to say that this requires the solving the inverse kinematics, let's say in the vision domain, something I did as a part of my PhD, just to show you that this is one part of that whole problem where probably the vision will allow you to do this kind of things. So, okay. So what we are doing, one of the important component in this whole aspect is okay, the manipulation, grasping, and manipulation is done, inverse kinematics is solved. One part is still is a very challenging, is called grasping. So far the current method relies on the models. That means you already know the exact model, where to grasp, and how to generate meshes, find the point of contact, and then go and grab it. So, but that is changing now with these sensors like the range sensors or depth sensors. What you can do is that I don't need to know what object it is. It is good enough for me if I know which are the graspable affordances, means which are the places you can grab simply. So probably if my width is like 2-finger gripper, I just say that grab at the neck or here or here. If I can do that, probably I do not need any a priori models.
Yes, sir. Yes, sir. We have taken care.
Okay, I don't have to learn all those models. This is a new way to look at things. So we don't need any a priori knowledge, and you can combine multiple sensors to do this. So we have done some work. Okay, so I'll just show you a video. So what we are doing is, so what is happening is that we have a Kinect here, and we have a small robot arm is there, and objects are there. My algorithm tells that these are the graspable points that it can grab. Okay, so once you do that, that part is done by the grasping module. After that, we solve the inverse kinematics, and the robot goes and plan the path and everything. It goes there, exactly grabs at the same point, picks up the item, puts in a box, that one. All right. So yeah. So this is one aspect. I'll also show you where it is applicable. Probably you know the e-commerce industry, right? You know about Flipkart, Amazon. You will be surprised to know that Amazon warehouses are completely automated, in the sense that they have thousands of Kiva systems that can pick up the racks and bring it to you. There are people in the last end where they pick up the items from those shelves, which are brought by the robots, and you put in the box, right? Then you pack it and ship it. So that part is still manual. So whenever there is a holiday season or a festival season, Amazon hires thousands of people just to fulfill their orders. Okay, so that part is still human, where it has to go and pick up from the rack. The rest of the things like which rack will come, when will come, everything is automated. So that has been done. Last puzzle is still not solved. Probably with this kind of technology, we'll solve that. If that happens, then there won't be a single person in the fulfillment center. The moment you press a button on your mobile app, and your product will be delivered all by robot. So there won't be now with the drones that they are employing, probably humans are not even required for shipping. It will be directly delivered. So I'll show you that video. This is another interesting video. So this is a new company, Fetch Robotics. Earlier it used to be Unbounded Robotics, that was bought up by this. I hope. what you saw here is that you place an order through the app. The moment you place the order, the robot goes, picks up the item, then another robot comes with a box, it puts over there, then it goes for packing and shipping, whatever you say. So this is where this is how the things are going to change very soon. Okay. Well, this is just a simple work that we did. We had one intern, he built a new snake robot. I'll just show it for fun without any motivation or anything. He did some work, we built it. We had a 3D printer. He designed everything. He did from scratch, simulation to building, printing, and everything he did. So what it can do is that it can move in a linear line. It can move sidewise. It can take a U-turn. So this is how it happens. So so it uses only two motors per segment to generate 3 kinds of motion. So this is a rectilinear, that means you move in a straight line. Then there will be other that you will move sidewise also. It will show. I hope that one. So everything was 3D printed in our lab. So this is how it moves sideways. If it has to move sideways. I hope that you know what is the use of snake robots. It can be used for surveillance, reconnaissance. You can rescue missions. All those things you can be used. Or let's say you pipe inspection, or you want to do something within the pipe. Probably you can send such kind of robots. So yeah. So this is what okay. And probably there is a turning it. Let take U-turn, but it's okay. You would completely turn U-turn. It takes time, but it does that. So you okay. So I'll finish this talk by showing another video from YouTube. It's very interesting video, and it's very interesting to watch. It's a very simple thing, but it looks very interesting. Just see.
This is your car. This is your toothbrush. These are your things. But these are the things that matter. And somewhere in between is this guy. Introducing Jibo, the world's first family robot. Say hi, Jibo.
Hi, Jibo.
Jibo helps everyone out throughout their day. He's the world's best cameraman. By intelligently tracking the action around him, he can independently take video and photos, so that you can put down your camera and be a part of the scene.
Jibo, take the picture.
He's a hands-free helper. You can talk to him, and he'll talk to you back, so you don't have to skip a beat.
Excuse me, Anne?
Yes, Jibo.
Melissa just sent a reminder that she's picking you up in half an hour to go grocery shopping.
Thanks, Jibo.
He's an entertainer and educator. Through interactive applications, Jibo can teach.
Let me in, or else I'll... And I'll... And I'll blow your house in.
Hey, where'd you go? There you are.
He's the closest thing to a real-life teleportation device. He can turn and look at whoever you want with a simple tap of your finger.
Check out my turkey dinner, Mom.
I wish you wouldn't eat that.
Hey, they make turkey pizza? I want turkey pizza.
And he's a platform, so his skills keep expanding. He'll be able to connect to your home.
Welcome home, Eric.
Hey, buddy. Can you order some takeout for me?
Sure thing. Chinese, as usual?
You know me so well.
And even be a great wingman.
You have a voice message from Ashley. Want to hear it?
Absolutely.
Hey, call me when you're home.
Better make that takeout for 2, Jibo.
We've dreamt of it for years, and now he's finally here. And he's not just an aluminum shell, nor is he just a 3-axis motor system. He's not even just a connected device. He's one of the family.
Shh. Good night, Jibo.
Jibo, this little bot of mine.
What
So what you can see that, just to tell you, this has only 3 degrees of freedom. So we do not need really very complex mechanism. You have a camera, you can run your, let's say, tracker algorithm, face recognition algorithm, voice response system. Today the Google voice engine is so good, right? So all these things you integrate and you have such an interesting application like this. You don't have to pick up your phone, you just talk to it, it will talk you back and other things. It's no more a fiction, it is coming out a commercial product. Another robot probably is the Pepper robot by Aldebaran Robotics that was bought by SoftBank right now. So they are also coming with this kind of emotional robot that can emotionally interact with people. It can respond to your moods, change its mood on its own, understand what we are going through. You can have a very engaging conversation with humans. So this is how the robotics are changing around us. I hope you enjoyed the talk and probably got some ideas for your future work. So you have questions, then I'll take them.
Yeah, but I have a copy of
Oh, Baxter robot. Yeah. No, I won't order. We are planning to order this UR5 robot because we are planning to participate UR5, Universal Robot 5. PR is very expensive, awfully expensive. That is in a crores and it is a useless robot. Like investing so much is not worth it. UR5 is an industrial robot, industrial arm actually. It's not the entire robot, it's an arm. We are planning to participate in Amazon Picking Challenge that happens at ICRA every year. So we are planning for the next year. I hope TCS approves the budget. So if they do that, we plan to participate in that context next year. So this has a robot arm and then you can do all those things. We could have gone with Baxter also, but Baxter is cheaper than the UR5, but this is very lighter. So we plan to mount it on a mobile base. So it will be a mobile manipulator. Just the fetch robotics you saw, something of that sort we can do. So that's the plan. So that's one project we plan to take up in 1 year time. So yeah. So Baxter is definitely a good one. Yeah. It's not a product. So it's we have the algorithms. You can download it and make your own robot, whatever platform you choose. So we are not making any product. Most of the things that I have shown has not gone into any product. So in that way, we are not very product-based company. So we do very open research. We take up our own problems. Most of the problems that you saw were conceptualized by myself itself. I chose a problem. Whenever I get a student, he decides to do something. We start from there, and that's how we work. So yeah.
Are you working with some crime detection kind of application or with this basic recognition and?
I am not doing, but there is certainly a group within TCS who will be doing that. So even 90% of the researchers I do not know, but I am sure that we are doing work in the security surveillance area we work. But that will be different group.
Are you open for having some kind of sponsoring research for that through some institutes and
we do it through MOU. We do it through MOU. So we have MOUs with most of the IITs. So if MOU is there, everything is possible. If MOU is not there, then I think it will take time. So it's that way. We, as such, we do not fund research directly the way the government does. But if we work together and there is a need at some point of time, definitely it can be done. But it cannot happen on this spot where you say that, look, I need a 10 lakh funding and do you want to do it? So in that way we do not work. Otherwise we have funded at many places. In fact, in IIT Bombay we have a complete research lab. In IIIT Hyderabad we have set up an entire research lab by TCS. It was done a couple of months back. So we have done a very big level of funding, but not the way you are telling. Yeah.
Any other question?
So the most important thing is the sensors which are used for detection. So the whole success of the robot applications will depend upon how intelligent the sensors are. So is the research going on in that direction to make the sensor itself very smart and intelligent, and even if one sensor is
only sensor I used in the whole of the work was a vision sensor. Okay, that was the most important component of all my research. So vision is something is very cheap. So that does not arise that one. But secondly, the question is right. If you have multiple sensors like touch sensors, now the temperature sensor, hundreds of sensors are there. Then definitely you will have to take care of the failures of those sensors, and redundancy you will have to build into the system to make it more robust. So yeah, every sensor you use, it has its own limitation, and you have to be aware of that. So we are not working in the area of sensors, we are not building sensors. Probably there is a group which works on MEMS, but again I am not aware of. Otherwise we are not as such working directly into sensors. Yeah. Yeah.
Sir, in programming by demonstration field, very less efforts have been made for industrial applications. And most of the approaches are still restricted to pick and place and some simple plots. So is there any effort for complex?
First of all, you got a research idea already. You yourself told that nobody has done it. Then the probability is a good starting point for you to explore and see if we can do something. Programming by demonstration is definitely a new area. A lot of people are working in this area. And as you said, yeah, this is a good opportunity for anyone to do PhD in that direction. A lot of things have to be done. And pick and place is the most common task we do. Yeah, but yes, as you know, the state of art matures, we will be able to do more complex tasks. For example, I hope you are aware of the DARPA challenge that concluded a few months back, and I think the Korean team won the first position. So the DARPA challenge includes all those challenges, like you have a humanoid robot that can go in a, disaster prone area and open the walls, open the door, cut out something, able to hold the tools. All those problems that you mentioned is ultimately going into that one. So in the first phase it was completely teleoperated. That means there was nothing automatic, but you had to do it remotely. But in the next phase probably it will be more automatic, and this whatever you are saying will play a major role. See, the training by demonstration is a way to reduce the training time. If you can show it, and then any layman can use it. Okay, but if you tell them to write a program to do it, it is more complex. So in that way, training by demonstration only facilitates training part. So it's definitely a new area, and people should explore this.
Swagat, you also want some people in your group, right?
Yes, we are looking for PhD students mostly. The masters we get through in campus placement. Okay, so but PhD we definitely need. If you have a good CV and decent publication, apply to me. That's there. We are definitely want to expand our group. And if you are finishing your PhD and have some decent publications, so you can get back to me, right? So. Anyway, I hope you had a good time, and it could lighten up the environment. I think it was a very exhaustive day for all of you. It's learning so many concepts. Okay, so thank you very much for being here.